also talk a little bit about the instruction set, probably on Thursday, although we've kind of already jumped into it some. So on Thursday, I may talk a little bit, I may go back and do a little more demo on like the OLED display. So, okay, listen up. Nobody can hear if we got multiple conversations. So if you're using the OLED display, I did put it on the board, but I don't know. I was about ready to slit my wrist yesterday. I downloaded the code from the web, but I didn't actually have a board, and so I soldered one together real quickly, and then it had some kind of problem, and it's like nothing worked. I couldn't figure out what was going on. So anyway, I downloaded the code that I had just copied directly from a working program to the Blackboard, downloaded it, and couldn't run it. Well, I went back and looked at it, and so I do realize that the code that I put on Blackboard was pre-packaged for XC8 2.0. And unfortunately, when it does that, it buries in there some user-specific information that sometimes causes problems, but usually it won't compile. And it did compile, and still didn't run. So I don't know. So I went back home, fired it up. Yes, it works fine. So I downloaded the file to my jump drive. Unfortunately, you can't upload to Blackboard. Sometimes it'll let you upload a zipped file, but it has a restriction on how many subdirectories and files, and I don't think it might. I actually didn't try it, so maybe I'll try uploading that zipped directory. But in any event, I do have code that absolutely worked yesterday, or last night, on my jump drive. So if you really need it, I can give it to you today on that. Or I will eventually re-upload the code to Blackboard. But I don't know. I'm not sure what's going on. You should be able to switch to XC8 1.45 and maybe it'll work, but it usually has to convert some things. So I don't know. So maybe it's probably a problem like that. I don't think it's a logical problem because I don't know. It works fine and I didn't change anything, but anyway. So I'll get the OLED thing sorted out, but I actually just haven't had any time at all to look at it. And I won't tonight either. So it'll be tomorrow night before I can really look at it, or maybe tomorrow afternoon. Haven't been able to get anything done in my office all week because I had a lot of students that needed stuff, so, which is fine, but it just means I can't make progress on some of the things that need to get done. Okay, so anyway, so I will sort that out. It does work, and what I did try and do is write a little graphical driver for it with some graphical functions, and some of them work, but some of them don't. And so anyway, so I haven't gotten the little graphic program, but the two fonts and the splash screen work fine, and there are quite a few controls for it. I think I counted them up. There's 23 or 24 registers you have to set. So but all that's in that code. But some of those registers do things like scroll the display, change the brightness, and things like that. So if you're using an OLED display, you can come by my office. Hopefully, maybe tomorrow afternoon, for sure, maybe Thursday, and I should be able to help you with that code if you're having problems getting it to run. Did anybody get the OLED code to run? Okay. So how many people are using an OLED display? Yeah, okay. So, but you haven't gotten any of the code to run. Okay. Well, it works. So I don't know what's the problem with the files on the web. I just haven't figured it out. It's probably because they were 2.0, XC8 2.0. Okay, so that's kind of the stuff going on. So we're going to talk more about the Freedom Board, and let's see, I already did this one. So we already got a little bit on this done. So and we talked about that. Okay, so we talked about that the Freedom Board has a Kinetis KL25Z 128, and it's VLK4, which has to do with package and speed stuff. It is an 80-pin low profile quad flat pack. It is a Kinetis L series device. It's not actually a K. The K stands for Kinetis L series. But there is a K series Kinetis line too. So this is the L series. And when you... Oh, sorry. Yeah, that'd be nice. So when you load it up in the in CodeWarrior, so the software we'll use is CodeWarrior 10.6, I think, so it's loaded on the computers in the lab, and maybe 10.5. I'm still using 10.5. I downloaded 11.0, but I can't get it to work. Or it's got problems. And I think I told you that Kinetis is going through this this internal gyrations because of their purchase by NXP. And eventually, the program that's going to run will be an NXP program that programs some of the other NXP chips, but it'll also, they're going to add the KO25Z, the Kinetis line to it too. And they have some of the Kinetis line added, but they don't have all of it. So anyway, so stand by for that, probably a few months. But in the meantime, we're going to use this legacy program, CodeWarrior 10.5 or 10.6, which eventually they're going to abandon and not support anymore. So that's kind of why it's in a little bit of a state of flux. All right, so anyway, so it does have this ARM core. It's an M0 plus core. So all the ARM cores are either A cores, R cores, or M cores. The A cores are kind of the big things like used in the Apple iPhone and things like that. The R cores are real-time data processing things, and the M core are for mobile devices. Obviously, the A cores are used in mobile devices too, but more like embedded devices, basically. So I don't know, mobile, embedded. Embedded and mobile aren't the same, obviously, but these are very low power. It's a very low power ARM, but very, very powerful. And so, anyway, this is a full 32-bit chip. It has a 32-bit data line, and just sort of incidentally, it also has 32-bit address line, which is actually crazy because it only has to address something on the order of maybe a seventh of a megabyte or a sixth of a megabyte. That's all it really needs for addressing. So the other zillions of megabytes aren't needed. But they use some of them. They do take some of the stuff and place it in multiple places. Like for instance, the routines to access the GPIO ports. They actually have identical set of registers for the ports in 2 different locations. And apparently, although it does not state this in the data sheet, apparently one set is this single cycle set that also does decorated loads and stores. And decorated loads and stores are single cycle but powerful commands where within part of the address you embed additional instructions for ANDing and ORing and doing some processing on the bits that you're actually addressing. I've never seen anywhere where the decorations are documented. So how you would use those is completely beyond me. I'm sure it must be someplace, but I haven't found it. And since I didn't really spend all that much time trying to figure it out, I haven't looked all over the web for it. So maybe it's out there someplace. It probably is. But in any event, it's not in the data sheets. So there's a lot of features that aren't even very well documented, or if they are documented, they're documented in such a way that it's not very easy to find the information. And that's when they talk about this single cycle fast I/O. That's what they're talking about. But the other ports are plenty fast because it can run at 48 megahertz. So that's a lot of instructions per second that it can execute. This chip has a built-in 128 kilobytes of flash for program memory, and it has 6 kilobytes of static RAM. So that's a pretty healthy amount of RAM and a very good amount of program memory. So you can really write a pretty complicated program. And then it has all these other things. We'll talk a little bit about the clocks. Hopefully, we'll talk about. I've already mentioned this. I know it has this phase lock loop and a frequency lock loop that allow it to take some basic clocks. Both an external clock can use the phase lock loop and the frequency lock loop, and an internal clock can use the frequency lock loop, and it can generate several different clocks. And we'll look at that oscillator. It also has built-in 4 meg and 32 kilohertz reference oscillators, and a built-in low-power 1 kilohertz RC oscillator that you can use for your computer operating properly watchdog timer, or for a real-time clock and some other things. Okay, and then it's got a bunch of peripherals and a bunch of stuff built onto the Freedom board itself. So the peripherals, it has a really nice, very capable A to D, 16 bits, which is nice. Our PIC only had a 10-bit A to D. It uses the same technology though, successive approximation register, but this one has the ability to average values, to look at thresholds, to look at values above and below thresholds or within zones or whatever, and automatically generate interrupts based on those values. So it's a very powerful A to D. And it has this really complicated circuit routine you need to go through to calibrate it. Every time you use it, you're supposed to recalibrate it, and then you store these new calibration values in registers, and so it can be pretty accurate. Even if you don't calibrate it, it's pretty accurate. But if you do the calibration, it's very accurate. And then there's a 12-bit D to A controller, so that's very nice. And a high-speed comparator. So those are the analog stuff, and then it's got a bunch of serial things, 2 SPI ports, 2 I2C ports, 3 UART things, and then it's got a full USB capability, so it can actually be a USB driver master. It's very nice. And then it's got this system tick timer and a low power timer and a bunch of other things. On the board is a 3-axis accelerometer, capacitive touch slider, RGB LED, and it's got these Arduino compatible I/O headers. The Arduino only has a single row of headers. This has a double row, so it's not really, the double row is not compatible, but the outer row is sort of Arduino compatible, although there's a voltage problem because most of the Arduinos ran at 5 and this ran at 3.3, so there's been a little problem with that. Okay, I'm not going to talk about the tower board. If you don't want to buy a 25Z, but you want to work by yourself, then you can use this tower board that has the exact same processor, but slightly different peripherals. All right, so the core is ARM, the peripherals are all Freescale and now NXP, and so that means you have to read different data sheets depending on whether you're looking at peripheral stuff or core stuff. And that makes it a pain in the butt. I talked a little bit about the ARM stuff. ARM has supplied cores now, maybe something like 14 or 16 billion cores to countless numbers of microprocessor manufacturers. So they're really out there in large numbers. Here's the block diagram. We've gone over this. It has this NVIC, nested vector interrupt controller. We talked about that. It has this very complicated wake up from sleep interface interrupt controller. And then it's got obviously the CPU stuff. The M0 Plus doesn't have hardware divide, doesn't have hardware multiply, doesn't have hardware floating point, but some of its bigger brothers do in this same product line. Like the M6 has a hardware multiply, and maybe even some floating point stuff, I'm not sure. So some of these other chips, and I'm sure there'll be more that'll come out in this product line that'll be even more powerful. And the 6 runs at a higher speed, and it's a little more powerful chip. And in that, they certainly did implement some of the real-time operating system functions like multiple stack pointers and things like that. It does have a memory protection unit that allows it to segment the memory and keep applications from bleeding over to other applications. And it's got this advanced high-speed bus light interface, and then this fancy GPIO driver that's not very well documented. And then it has some really nice built-in debug capability, so that you don't have to recompile for debug, and then when you don't want to use debug, you can compile for production. This one, every time you compile, you always have the debug available if you have an interface that supports it. And it does take. There are definitely some pins used for this, but it's not too bad. It doesn't take maybe as much as the PIC does. All right. So anyway, so I think I've talked about all this. It is compatible. The instruction set's compatible with the ARM Cortex M0 and with a subset of the M3, M4 stuff. So you can reuse existing compilers and debug tools and all that. So, okay. So I know, Carrot, you should kind of be vaguely aware of most of those things, but the stuff I want you to know. So it does have, you don't have to memorize the number, but you should know that it has in the order of about 50 or 60 instructions. Turns out it has 56 instructions. You should know that the programmer's model has 17 registers, 13 general purpose registers, including the low 8 registers that all the instructions can access, and then the high 5 registers that only some instructions can access. And then, in addition to those 13, there are 4 other registers. There's the program counter, there's the status register, there's the stack pointer, and there's a thing called a link register. So those are the 4. You should know that. You should know these 17 registers. On our chip, they did not increment 2 different stack pointers. They only implemented 1. So it's not really optimized for an operating system, which is fine, because generally, if you're going to do an OS, you probably have a little slightly more powerful chip. You can add all the memory. So all the memory, of which there's 6 kilobytes of RAM, static RAM, and 120 kilobytes of flash. Every one of those locations is an 8-bit location. So for a 16-bit instruction, you need 2 locations. So the program counter would load all 16 bits at once, but it would be incremented by 2 to point to the next half word. You can also move 4 bytes at the same time. So you can move 1 byte, 2 bytes, or 4 bytes at the same time, and then you can move multiple words in memory too with special instructions. So the memory, every location in the 4 gigabyte address space, 32 bits, 4 gigabyte address space, addresses 8 bits. But if you want to address 2 bytes and use an instruction that can move 2 bytes at once, called a half word, then you have to make sure it's an even address. It can't be an odd address, and that would be a misregistered, misaligned half word. So you have to have half word aligned, even addresses, and then you also have to have full word, which is 4 8-bit bytes. They have to be aligned on address 0, 4, 8, C, or is it C? Let's see, 8, and, 9, 10, 11, 12, and C are back to, yeah, so 4, 0, 4, 8 are C. It has to be, the lower 4 bits have to be one of those addresses. If you tried to move a full word, but your address was odd, or your address was anything other than 0, your lower byte was anything, your lower nibble was anything less than different than 0, 4, 8, or C, it would generate a system error, and it would stop the program. So it does have this linear 4 gigabyte address space, which is really nice because that means there's no bank registers, there's no paging. It does simplify the software, so that's really nice. And then of course you have many other manufacturers making chips with an ARM Cortex-M0 Plus core. So at least you can, they talk the same assembly language. And even though we're going to write it, all our code in C, you should have some sense of, a lot of the tools you can use on another manufacturer's chip and also on this chip. But there are problems with the peripherals. You may not have good library support and other things. So it's not as straightforward as it might sound. Again, it has great debug capabilities, including this trace buffer. So you can actually have it store some number of instructions, and you can go back and look at them after it's run and see potentially where problems are. So it's another really good debug tool. And then this bit manipulation engine, again, I mentioned that. I don't really know how to use this, so I just use the standard registers, but it's apparently out there and available. And then it does have DMA. I know one of the students was talking to me about using DMA on their senior design stuff. So apparently it's not that difficult to use, and there are examples on the web. We probably, the plan, we're not going to use it on the 2 labs we're going to do. They're going to be straightforward labs. But one of the real bragging points for this chip is its ability in sleep modes to get down to very low power. And that's one of the reasons why this has been such a popular core. All right. And I think Freescale was one of the very first ones out with it. They also happen to have this really nice flash memory that was also very low power. And so when they married them together, they really had a real competitive chip. And that's one of the reasons why NXP is continuing this product line. Okay, I think we talked about most of this stuff. So I'm not going to review this. And we did this. So again, to review the programmer's model, we went over it. 13 general purpose registers, which include the low 8 and the upper 5. All instructions can get to the low 8, only some can get to the upper 5. And so they're labeled R0 through R12. Then there is a stack pointer that's 13. The ARM core itself supports 2, but only 1 was implemented. And then you have the link register. I'm not really sure exactly what it does, but it says here it stores the return information for subroutines, function calls, and exceptions. Okay, fine. But since you can nest these things, obviously it can only store one return pointer, so it's a little confusing just how this gets used and what happens. And maybe its contents gets pushed to, and I don't know. Anyway, it's a little confusing, but that's what the data says, and that's about all I've read about it. The program counter, again, keeps track of where you are in the program. Anytime you jump or interrupt or call a function, it changes to the new location. Otherwise, it just updates by the size of the instruction. There are 56 instructions. 50 of the instructions are 16-bit instructions, and the other 6 are 32-bit instructions. So the program counter is either going to update by 2 or by 4, depending on whether it's one of the 32-bit instructions or one of the 16-bit instructions. And then it has this status register. And the status register is broken down into these 3 different registers, but they're really all in one 32-bit field. And so there's a field in there that gives you this 4 status bits: 0, negative, carry bit, and the V bit, which is 2's complement overflow bit. Then there's also an interrupt field, and then there's another register, this execution program status register. And what that does, there's a bit in there that, not in this chip, but in other chips in this family line, allow you to change that bit and actually change which assembly language instruction set the chip is going to run on. So you can actually change that on the fly. You can have one set of assembly instructions, and then there's a whole other set you can also have. But our chip only supports one set, and that's the Thumb M0 Plus. So if you change that bit, the chip will probably stop working. Then you'd have to reboot it, or maybe turn it on and off even. Okay, and then there's some other things. There's a control register which controls the stack used. Well, we only have one stack, so we don't really have that. And then there's a PriMask that it basically masks what interrupts can occur in terms of exceptions like divide by 0, misaligned loads and stores, and things like that. And you can apparently turn this on and off. I don't even know if this is implemented. Again, some of the documentation is just not very helpful. Okay, and then there's a few other registers. I'm not going to talk about any of them. We went through the NVIC already. Nested Vector Interrupt Controller. Remember, nested meant you could have different levels of priority. There are 4 different levels of assignable priority. And if you assign a low level of priority to one interrupt, during the time that interrupt's being executed, if you've assigned a higher level of priority to another interrupt, then it can interrupt the low-level interrupt. If it's the same level, it waits till that interrupt's completed, and then it re-interrupts and executes the second interrupt. But if it's a higher level, it will interrupt the lower-level interrupt. And you can have, the interrupts can be level sensitive or edge sensitive, and then there's all sorts of wake-up features and sleep modes. It has several different levels of sleep and a number of various ways to wake it up from different levels of sleep. You can move the vector, so it's also, the interrupt is vectored, which means that every interrupt has a unique address for that particular cause to go to and be executed. And the way this table is implemented, by default, all the entries in the table are these things called weak aliases, and they're all just dummy code that basically just returns from the interrupt and doesn't do anything. But I think it's maybe clear the bit or something. But if you write a routine with that same name, then your routine will be substituted for the weak alias in the interrupt table, and then it will call your routine instead of the dummy routine in the interrupt table. So that's the vector. So there's a vector in a table that points to the specific interrupt for each specific interrupt causes. So that's the nested and the vector part of the NVIC. All right. And there's this really good debug support, 0 to 4 hardware breakpoints, 0 to 2 watch points, and then you can, there's a program counter, sampling register, and a whole bunch of things you can do. It's very nice. A lot of these do require a slightly better interface than the one we have. We're going to use the OpenSDA, and that's a fairly generic interface. It's based on the chip on the board, but some of these features are not available on that. But if you have a little fancier interface device, then some of these features are quite nice. Like you can set a watch variable, but you don't even have to stop the processor to have that value update. It will update in real time for you. It's a really nice feature, but I've actually not seen that work because it takes a little better interface device than we have. Okay, and so we have this bus. So yeah, I'm not going to say much about this. It's a pretty powerful bus. Again, remember we have two 32-bit buses on here. One 32-bit address bus and one 32-bit data bus. So they're pretty big buses. And then we talked about the single cycle I/O port stuff. Again, I just use the standard GPIO registers, and they work very fast. There apparently is something you can do that's a little more exotic with these decorated loads and stores that execute with the BME in single cycle mode, but it's so poorly documented, I've never really figured out even where it is, much less how to use it. So I haven't really tracked that down, but you're more than welcome to sort that out for yourself. Okay, so the actual instruction set, we usually refer to it as thumb, but it's actually ARM v6-M thumb. That's the official name. And so anyway, I guess they do have a 32-bit hardware multiplier. Yeah, I guess so. I'm not sure if that's actually implemented on this chip, but since C worries about that and takes care of it on its own, you don't really have to worry about it. But in assembly language, you would. When you integrate the ARM core to your peripherals, you have to make a decision on whether you're going to use little endian or the big endian approach. And Freescale chose little endian, so that's how it's implemented. So all the things are in little endian. And I don't even like to talk about this because it's confusing. Most things in the world are little endian. If you find something that isn't little endian, tell them to go buy something else because you don't like to deal with big endian. But in any event, all it is how the bytes are stored in a 32-bit word, and the bytes are stored with the low order byte first, the next order byte next, and the next order byte next, and the higher byte last in big endian, in little endian form. In big endian, it's just the reverse. So it only really refers not to the bits within a byte, but to the order of bytes within a word. And specifically a half word and a full word. If you're only addressing 8 bits, then little endian and big endian are the same. It does have some really good latency interrupt handling. So the latency is very fixed. You can be very confident how long from when the interrupt is raised to when you're going to actually start executing code. There's very little variability in that, and that's really nice. That means there's minimal jitter when you're using the interrupt to sample things or to do things. But even independent of that, your A to D module can be programmed to automatically continue updating to initiate new scans, even at different addresses, and take the data and automatically store it in memory using DMA. So really, so for sampling, if you really wanted to do it optimally, you just do it all in hardware and then you go read it when you wanted to. So, but it is nice, maybe for other things, that you can have this very predictable interrupt latency. And then it does not have privileged and unprivileged support. That was not implemented on this chip. It is available in the core, not implemented on the KL25Z. Okay, and then again, it has lots of sleep modes, and the interrupt handler allows you to use just pure C functions if you want. Obviously, assembly language is one of the places, interrupt handlers are one of the places where you might actually choose to do assembly language, just because in an interrupt program, in some cases, you want it to be absolutely as tight as possible. And so in that setting, even in an optimizing compiler, you might be able to write a tighter piece of code in assembly than the compiler can optimize to, for shorthand. But the 6 instructions that have these, that are 32-bit, are these, and here's their names: BL, DMB, DSB, ISB, MRS, and MSR. So not to worry about them. Since we're not really going to write any code in assembly, I just kind of want you to have a loose working knowledge of, about how many instructions. 56, you don't have to remember 56, but if I ask you, is it closer to 50 than it is to 30 or to 100, you should know, yeah, it's closer to 50. So it does implement the competing for some of the higher level chips. The ARM V7M is the assembly language instructions, and it implements all of the 16-bit instructions from this instruction set except for these. So that's why it's pretty upward compatible for even bigger chips. If you write code in this that works on the KL25Z, they will almost for sure work on these higher level processors. You might be able to benefit from some instructions you don't have on this chip, but all the instructions on this chip can be used on the other one. All right, so we'll just take a quick look at the instruction set. I'm not going to spend a lot of time on this. I just kind of want you to know a little bit about it. Just seen this once. I'm not going to go back and ask you any particular test question related to any of these details at all. This is more just for information purposes. So we have logical instructions and shift instructions. So the logical, there's an AND, an XOR, an OR, a bit clear, a move, and an AND test, or a move not actually. There's a shift left by some number of bits, shift left by some value in a register, and then shift right by some number within the instruction called shift right by immediate, shift right by register. And then there's arithmetic shift right. There is no arithmetic shift left. And there's arithmetic shift right by register. And then there's rotate right by register. There is no rotate left. And so you can see some of these things, there is a logical shift left and right. But a lot of times in a more complex instruction set, there'll be a shift, an arithmetic shift left and a rotate left, but they don't include those. And that's mostly because this instruction set was written to support C assembly or C compile. It wasn't really written to be hand-coded in assembly. And then we have load instructions. Now this is really interesting. So notice we have, so remember there are some instructions like the adds, I guess, and some others where you can actually address 3 memory locations. But you only have 16 bits to do that in. So obviously you don't have room for 32 bits of address for 3 locations plus an opcode in 16 bits. You don't even have enough room for one 32-bit address. So all of the instructions are using registers, and so the register number's in the instruction, but that's it. And so you can reference 3 registers and have an opcode. That you can do. And so almost all these things are based on values in registers. And then what they do, in some cases, they have an offset built into the instruction. So you reference a register as kind of the base address. Maybe you have 4 or 5 variables, and so you index to the variable using the base address and an immediate offset in your instruction. And that way you don't have to continue to load a bunch of addresses in your indirect register that you're using. So you have to have a register number, and then you have this immediate offset in the instruction. And you have these for, almost all these are based on 3 different things: word, half word, and byte. So 1 byte, 2 bytes, 4 bytes. And remember, the word and half word have to be appropriately aligned in memory. So the half word has to be at only even addresses, and the word has to be at only addresses that end in the last 4 bits have to either be 0, 4, 8, or C in hex. Okay. So you have a word with an immediate offset, half word or byte. You have a word with a register offset, so you reference 1 register for the address and another register for the offset. and so word, half word, and then anytime you get whenever you move less than 32 bits into a register, we also have to worry about whether it's signed or unsigned. And so that's why we have a half-word register offset and a signed half-word register offset. And we also have a byte register offset and a signed byte register offset. So in this case, you're moving a byte into a register. Well, what are you going to do with the other 3 bytes for which there's space in that register? Because all the registers are 32 bits. Are you just going to leave junk there? No, you're going to either sign extend or 0 extend those remaining 3 bytes. In the case of a half word, you've got 2 bytes you're moving, but what about the upper 2 bytes? Are you either going to sign extend if it's signed, or are you going to 0 extend if it's a half word? So that's why it works like that. And then sometimes you can only, in some cases you may only move 8 bits and leave the other parts, or 16 bits and leave the other bytes unchanged within that register. And then you can also move stuff referencing the program counter or using the stack pointer. And you can also include, in some of these there's offsets. With the stack pointer there's an immediate offset that's available there. And then and here there's a label that's relative to the PC. And then you can also move multiple bytes starting from a base register, excluding the base or including the base. And then we have so those are the load operations where you're taking information and putting it in a register. And then you have the store operations. And you don't have to worry so much about sign extend, because the store operations, if they refer to a byte, you're only moving 8 bits and you're not screwing around with the other nearby bytes. When you move a half word, you're only moving 2 bytes and you're not messing with any other bytes. When you move a word, you're moving 4 bytes. And again, leaving all the other surrounding bytes unchanged. So you don't have sign extension or 0 extended in that case. So we can move the word, the half word, and the byte. We can do it with an offset stored within the instruction, or we can do it with an offset preloaded in a register that is added to another register to generate the indirect address to do the store. And then we can store relative to the stack pointer, and then you can also move multiple bytes where you can have a list within a register, or you have several registers that you're referencing, and you can move those bytes. Because we have a relocatable stack, there is a push instruction, and apparently this push with link register, not really sure exactly how that works, but apparently involves the link register in this process. And then there's a push just by itself. There's a pop, and then there's a pop with return. So the pop with return is the 32 bits is popped off the stack pointer and put in the program counter, and then that gives you a transition to that new address. And that's typically what you do returning from a subroutine, for instance, where you store the return address, or function, where you store the return address on the stack pointer, on the stack, and when you pop, it pulls that return address off, puts it in the program counter, and that effectively transfers you back to your mainline program. And then we have branches. And these branches can be conditional, and there's 2 additional codes that go with it, and then you branch to some labeled address. And we'll look at those other codes. The unconditional branch, you just have the address you're going to, the label, and then you can use the link register. I'm not exactly sure what that means, and it has a label. And then there's a branch with exchange, and with link and exchange, I don't really know what's going on with those. Those are, I think, C things that C uses and not typically used in standard hand-coded stuff. So you can take a byte in a register and sign extend it, or a half word and extend that. And you can do whether it's signed half word or signed byte, or unsigned half word or unsigned byte. So when you extend these, it just fills up the remaining register either with the sign in the case of signed, or with zeros in the case of unsigned. and then you can switch bytes in a word, you can switch bytes in a half word, and you can do part of a half word. I'm not exactly, I haven't really used this, but this is just a way to reverse the bytes. Okay, then you have some of these special things. Supervisor call, that's basically a software interrupt. You can enable and disable interrupts, and you can do, you can get to some of the special registers, like the status the register with the status bits in it. Some of those other registers you can get to as well to look at interrupts and screw around with the interrupt bits in there. And you can also create breakpoints in software. So there's several other things that are kind of system stuff. This send event, wait for interrupt. Some of these are actually sleep commands effectively. So wait for event puts the processor into sleep mode and then waits for the wake up event and so forth. Wait for interrupt, same idea. And then there's a no-op. I don't know what the yield is again. Unless you write code in this that's fairly complicated, you're not going to use this. This is, again, C can use this, but you don't have to as a C programmer. And then this instruction synchronization, data memory, and data sync. All right, so those are the instructions. And again, 56 instructions, most of them 16-bit instructions, 6 32-bit instructions. All of them can get to the lower 8-bit registers. Only a few can get to the upper 5 general-purpose registers. And then only some of them can get to program counter, stack pointer, and things like that. All right. Any questions about the instruction set? So that's kind of a little overview, just so you kind of have heard it. I probably won't ask you anything detailed about it, other than you should know it has loads and stores. There is a place where it goes over all the different condition codes for the branch, and I don't see that in here. Let's see. Let me see. I think there, and it's really a nice feature. If you remember when you were writing assembly language instructions on the PIC, you well here's this status register. Again, it's 32 bits. The only bits that are part of the status register, part of that register, are the upper 4 bits, 31, 30, 29, and 28. And it's N0, so negative, 0, carry, and V, 2's complement overflow. Okay? And so this was little endian. So little endian, low order byte, next byte, next byte, next byte, in that order. Big endian is the opposite. So anyway, let's see. I want to. Well, this gives you a little. Yeah, let me go over this. So this gives you a little bit of an idea. So again, we have 32 gigabytes of address space. That's a lot of address space. And so this is how it's more or less carved up. But again, remember, 128 kilobytes of flash, 6 kilobytes of static RAM. So that's what? 134 kilobytes of actual memory, and then throw in maybe a couple of kilobytes of register addresses for the various modules. So so now you're maybe tops you're up to maybe 140 kilobytes, and you have 4 gigs of space. So it's kind of there's a lot of empty space, unused addresses. But generally, the way this works is code would be from 0 to 0 to 00000 minus 1, okay, or 1 FFFFF, and then from 2 to 1 less than 4 is the static RAM. So flash here, static RAM here, and then peripheral stuff from 4 to 5 or 4 to 6 effectively. But you still got from 6 to 8, 8 to 10, 10 to 12, 12 to 14, and 14 to 16 or whatever. So it's really it's a lot of space. There's a little bit up here at the system level. And somewhere in here we have the GPIO ports for the standard access, and then the GPIO ports for the fast access. And I guess they're both in this range. but they're quite a distance apart. But you can see there's a lot of address space to be used. And then you could add additional RAM up here for some fancy, like write-through cache stuff and write-back. Those are pretty advanced things, and I think all our RAM is in this range. That's where our static RAM is. But you could have peripheral RAM interface to be at some of those other spaces, I guess. All right, so anyway, again, most of the 16-bit instructions can only access 8 of the general purpose registers, R0 through R7, and they're known as the low registers. I'd like you to know that. A small number of the 16-bit instructions can access the high registers, R5 through R15. And then we have this conditional execution using these 16 conditional branch instructions. The branch range is only plus or minus 256 and 254, plus 254 minus 256. It's probably, yeah, anyway. And it's based on these NZCB flags, the status flags. Okay, so here's, I think I have those laid out here. Yeah, so there's BL, no, let's see. Yeah, here they are. No, sorry. Well, actually, there's some more instructions. We didn't talk about add with carry, add, and, clear, compare, negate, exclusive or, bitwise, bitwise not, bitwise or, reverse subtract, carry, subtract with carry, and subtract. And then we looked at these, the shift, the logical, arithmetic, and rotates. We looked at those. But the one I want to get to here is the condition codes, which I think we have. Right. Yeah. Here are the condition codes. So these are all set up with a B in front and then the 2-digit code. So at BEQ, branch equal, BNE, branch not equal, and so forth. This is really nice. So at the assembly language level, we have all these different conditional branching codes. And here's the one point I want you to know. I might ask you about this. So we have to differentiate. So when you write, if you were to write a routine in assembly, and to some extent, even when you use C, you need to keep straight on whether you're using a variable as a signed value or an unsigned value. Now in C you have to specify that, but it doesn't mean you have to remember what you specified and use it that way. You can still use it appropriately. And the classic case of that is you just declare an int, say int j, and then you set up a for loop with j in it, and you want to let the for loop go up to 50,000. Turns out, by default, j is unsigned 32 bits. Unsigned 32 bits by default can't get, or actually unsigned 16 bits maybe. By default, an unsigned 16-bit can't get over 65. Can't get over 32,000. So if it's 32 bits, it's only going to count to 32,000, and then it's going to become negative, and that's going to screw up your test. And so because C considers it to be signed, and it is signed by default. If you don't specify, it's signed. So if you want it to be an unsigned, you have to specify that. And so anyway, keep those things in mind. But it's really nice to have all these built-in tests. Now again, we're not going to use these because we're going to write in C. But it's nice that C can write much more efficient code because it has all this conditional branching available to it. And the point again I want you to see is some of this conditional branching is specifically unsigned. So unsigned higher. So our unsigned higher and equal compared to signed greater than. Okay, so notice unsigned higher, it looks for the carry bit to be a 1 and the Z bit to be a 0. Signed greater than, on the other hand, wants the Z bit to be a 0 and the N bit to equal the V bit. Okay? So you can see these things are more complicated, and they are definitely broken out by whether you consider the value that you're working with to be signed or unsigned. Now in C, you do have to declare it, but you don't have to remember what you declared, nor do you have to use it properly. In assembly, you don't get to declare it. You just have to know what you intend it to be and use it appropriately. And so there's a lot of pressure on you if you were to write in assembly to use your signed and unsigned variables appropriately and to use the right branching, conditional branching codes to make that work out the way you intended it to. Does everybody understand the distinction I'm pointing to here? I have a feeling maybe this is going over your head. Okay, so you see, for instance, for equal, it's not particularly difficult. It does a subtract and then make sure that z equals 0. Or z equals 1, which means 0. So if you subtract and it's not 0, then z will be 0, and that's consistent with not equal. But when you do greater and less than, higher, we don't say greater than, we say higher for unsigned, and for signed we say less than and greater than. And so you can do less than or equal and various things. Anyway, not all the things are supported. Unsigned, lower, or same. Anyway, so you can see not everything's supported, but there's a really nice selection that you can get to choose from. Okay, I did want to talk about that briefly. All right, so back here. Okay, so that's pretty much the instruction set. And then I think there's a little part on the clocks I wanted to talk about. Let's see. So let me talk about the lab a little bit. Okay, so this is code, more or less the code from the lab. Now, a couple of things on, so the first lab is just blinking some of the colors in the RGB LED. Okay, so when we wrote the original labs, we actually mostly used the tower boards. That was the original intent. We were going to use the tower system. It's got these little elevators that click on the side, and there's extra boards you can put in. And anyway, it turned out right after we started with that, the Freedom board came out, much better thing, and so we kind of abandoned the tower boards, even though I have a whole bunch of them. So some of the labs were written for the tower board. So the values that are set up for the tower board, and that's fine if you use the tower board, it'll work. But some of the code that's on the web that you download as your starter code has the wrong values in it. So just remember, when you want to blink a red LED, you have to make sure that you've got the right location. And there's a little, if we go online, let me show you where that is. So in the lab on Friday, when you screw around with this, and I guess I should go over there and make sure that CodeWire is actually on those machines. So let's see, Blackboard. So let me pull up Micro 2, or no, Micro 1 rather. Okay. Yeah, so if we go down to the KL25Z labs, it's a different directory here. And then you look at the top of this. So there's a Word file called LED locations. Pull that up and look at that. You might even want to print that out before you come to lab. It's just one page. But it points out the difference between the Freedom board and the tower board. So the Freedom board has, the red is at port B, pin 18, and on the tower board, you don't actually have an RGB LED. You've got 4 LEDs, an orange one, a yellow one, a green one, and a red one, all separate. And they're where they're located. So some of the code may have PTA and PTA 17 and PTA 16 and PTA 5 actually listed as the assignments, and you'll need to fix that because your RGB LED, the blue is PTB1, the red is PTB18, and the green is PTB19. Okay, so that's available. You can go find it. All right, let's go back and look at the code, which I uploaded here. And I just want to point out a few things. And so they set some stuff up, and I think Bob Apolloni actually wrote this, and did it sort of fancy, but then not really. So this is actually, this is set up for 16. So these are set up for the tower board. So if these are the numbers, they're wrong. And interestingly, you notice where red is defined as 5, and green is 16, and blue is 1. It turns out that we never really use red, green, and blue individually. We use this blue shift and red shift and green shift though. So we define these functions, read off, read on, read toggle, as GPIO-A underscore pin set output register equals read shift. And so this just references the bit, the proper bit within GPIO-A. But actually, if you go back and look at that Word file, none of the LEDs, none of the RGB LEDs are in port A. This is for the tower board. So you'll have to fix all these things. What I want to point out though, and remember, these are the special instructions, and we've talked about this. Every single port A, B, C, D, and E, for all 32 bits, even though many of them are not implemented at all, have this pin set output register. And in the case of GPIO-A, or B, or C, or D, or E, the pin set output. So there's a pin set output register, there's a pin clear output register, and there's a pin toggle output register. And all you have to do is have a 1 in a mask that's in the position of the bit you're interested in affecting, and it'll either, with this one, it will set it, this one will clear it, and this one will toggle it at that position. So that's where the red shift comes in, because that specifies the bit position of the GPIO pin that's connected to the red LED on the tower board in this case. So you'd have to change that number up here, so the red shift was 18, or 19, or whichever it is, and then you'd have to change GPIO-A to GPIO-B, otherwise it's the same. Okay, so what I want to point out though is where we actually initialize everything. And so here's the initialization routine, and again, I think this is set up for the tower board. Although this is PTP18, so that is the red LED on the KL25Z. So they're sort of mixed around. Okay, so a couple of things have to happen for you to use any GPIO port. And it is much more complicated, or it is more complicated, maybe much more is even exaggerated, but it's more complicated than with the KL25Z. On the KL25Z, you just have to make sure that the TRIS register is set correctly, and if you're using it as an input, then you also need to make sure the AND-cell bit's turned off if in fact it isn't one of the analog capable pins. And then you're okay, and you just have to remember to use the port command to read it, and the latch command or the port command to set it for high or low. Okay, so on this it's a little different. The first thing you have to do before you can do anything with any of the GPIO ports is you have to turn on the clock to that port. And there is a separate bit in a special register for each port. There's a bit for port A, a bit for port B, and so forth. And then there are other bits that turn on and off other functionality on this chip. And the reason they have this is because they shut the clocks down to everything except just the stuff you're using. And with that clock shut down, it uses less power. So it's a nice feature, but it does mean if you're going to configure a GPIO port, the first thing you have to do is turn the clock on to that port. Just one bit for the whole port, but there is a different bit for each port. So, and there's a mask, so you don't actually have to remember where that bit is. You just have to remember that it is in what's called the System Integration Module underscore System Clock Gate Control Register 5. Now, you might think there would be System Clock Gate Control Register 0, 1, 2, 3, 4, 5, and maybe some more. Turns out that's not true. There is System Clock Gate Control Register 4, 5, 6, and 7. But that's it. There is no 1, 2, 3 or 0, and there is nothing after 7. So why they pick those numbers, I don't know, but that's how it is. So you can find this all in the data sheet under the SIM chapter. But it's easier just to sort of pay attention and switch the right things. So you don't have to have the 5 is the register for all the GPIO ports. So don't change the 5. But you do have to change the port A mask to port B if you want to turn on port B, and port D if you want to turn on port D. And then here we're going to set PTP18 to GPIO mode. Okay, so every pin, and every pin has the port output register for either pin set, pin clear, or pin toggle. And then there's also a pin control register for every pin in every register, all 32 pins, even though not all of them are implemented. And so, in this case, now, let me just show you the data sheets and whatnot. These are on the web, but they're also here, I think. Let's see the main files. Well, actually, I may have them. They're on the web, but they're on Blackboard, but I didn't put them down. So there's one called the KL25P80M48S FORM, and this is the full reference manual. It's 807 pages, and it references these chips, which include our, and for some reason they have an M in front of the K. It's the KL25Z128VLK4. So that's our chip right there. And if you go down here to, there's several chapters that we're interested in. So one chapter is 10, and that's where the multiplexing information is. It takes a long time to figure this out. But anyway, if you scroll down, you will find the multiplexing table. This is basically the only place where you can figure out what each pin can do. And it turns out every pin has several options it can have. The maximum possibilities would be 8, Alt 0 through Alt 7, but most of them don't have 8 different functions. In fact, I don't know if any of them have 8 different functions. Most of them have, 3 or 4 or 6. That's about it. So, for instance, every pin is named based on its port. So, and then depending on your package, there's a number on the pin too, which corresponds to its position on the periphery of the chip. So this is pin 1, 2, and so forth, all the way down to pin 80, because this is an 80-pin low-profile quad flat pack. So that's the 80 LQFP. Okay, so if we go back here and we look at a few of these pins, you can see, so pin E, 0. So port E, pin 0, and by default it's disabled. So it has no Alt 0 function, which would be its default function. But if you select Alt 1, then it'll be in GPIO mode. And that's true for all the GPIO pins. Alt 1 is always the GPIO mode. Then you can also select Alt 3, and it's the transmit for UART 1. You can select Alt 4, and it's the real-time clock out. You can select Alt 5, and it's the comparator 0 output. And then you can select Alt 6, and it's the I2C1 module SDA line. Okay, so it has all those potential functions, but it actually has no default function. And that's because all the Alt zeros are the analog functions, and they're all analog by default. Just like on the PIC, they boot up in analog mode. You have to take them out of analog to use them as GPIO. And so you have to change this. So when you want to use a pin as GPIO, you have to select this multiplexer setting to 1, Alt 1. Okay, so if we go back to the slides, and we look at that, you can see right here, port A underscore pin control register, and then 5. Don't confuse this with system block K control register 5. The 5s don't have anything to do with each other. This happened to be for the tower board that has A5 has one of the colors on it for some reason. Anyway, so in your code you'd have to put in port A underscore PCR 18, and then you'd also do port A underscore PCR 19, and then port D underscore PCR 1, because your RBG LED lights are on B18, B19, and D1. And then out here you would have port underscore PCR underscore multiplex paren 1 close paren. This is a macro that gets the correct mask generated to put a 1 in the 3-bit multiplexer field of the pin control register for that pin. Okay? So you can see, somewhat complicated, right? And you actually have to dig out that data sheet. So if you want to say, I'd like to use this function, you have to go through the data sheet and find what pins it could appear on, and then you have to set that multiplexer setting for the right multiplexer function. And this is how you do it. Okay, now that you've gotten Now you turn on the clock to the port, you set the port to be GPIO, now you can actually set the pin. In this case, we do GPIO-A pin set output register. Remember, we have for all 5 ports, A, B, C, D, E, we have 3 pin output registers. A pin set output register, a pin clear output register, and a pin toggle output register. Now, what's confusing is there's a register for port A for every pin that's 32 bits wide, but most of it's not used. But there's a field for interrupts, a DMA function, there's a field for its multiplexer setting, there's a field for whether it's going to have a high slew rate, a slow slew rate, pull-ups, pull-downs, whether the interrupts are turned on and off, and a couple other things. And drive levels, stuff like that. And so, but that's for every pin. But then for this pin set, you have one register for all 32 pins in port A. So sometimes you have 32 bits that covers all the register, and sometimes you have a 32-bit register for each pin. Okay? So that's a little confusing, but that's how it is. And then, so anyway, and then actually, believe it or not, within the this port A pin control register, there are 2 registers that let you configure half of the pins with each of the registers to use 2 registers to configure all the pins within that port to do certain things. So you can set all the multiplexer settings at once, all the interrupt functions and DMA stuff. But anyway, okay, so in this one, we have a pin set, a pin clear, and a pin toggle output register. And all you have to do, and you OR equal, you always use OR equal, and you always put a 1 where you want the action. Remember, when we wanted to clear a bit, we would have to do AND equal and put a 0 where we wanted to clear a bit and 1s for everything else where we wanted to leave them alone. But this is nice. You don't have to have an inverted mask for the clearing. All the masks use 1s where you want to have the effect. So you can change all the bits you want to change with a 1 in that bit position. But the only way to do this intelligently is to create a mask. Just the standard exact way we did it before. So we're almost done. Let me just take 1 minute. We'll talk about the mask here. And then I'll spare you the pain. I see I managed to put a number of people to sleep, but that's okay. All right. So remember, so it might be a good time to wake up and pay attention to the last minute here. When you do a mask for an 8-bit byte, it's not a big deal. You can just kind of figure it out in your head. Let's say in an 8-bit byte, you wanted to set bits, say 6 and 2. Well, I know that would be 0x40. Well, let's see, 0, 1, 2, yeah, 40, so 1, 2, 4. So that'd be, actually, that'd be, yeah, it'd be 44, okay? 0x44. So I can do that kind of in my head. Actually, I struggle with it. I usually write it down so I don't screw it up. But if I want to set bits, say, 23 and 17 and 11, okay, what's my hex number for that? It's a real pain in the butt to calculate that. There's a much easier way to do it, and we covered this in logic design briefly, but now I want you to learn it. I will ask you questions that involve using this construct, and you need to be able to do it because it's important for you to learn it. So I'm going to kind of force you. Okay, so let's say 23, 17, 11. So here's how we would do it. We create a mask, or you don't even have to do the mask. Let's say we'll do pin set, we'll do port B underscore pins, we'll do pin clear. Pin clear, output register, or equals. Now we want to clear. Let's say we want to clear pin 20, bit 23, 17, and 11. Those pins, we want those pins to output zeros. We don't affect anything else in port B. So what we want to do then is create a mask that does that. And the nice thing is we can use the OR equals, we don't have to use the ampersand equals, we don't have to invert our mask. We just have to create a mask, and we're going to do 1 shifted 23 times, ORed with 1 shifted 17 times, ORed with bitwise ORed, by the way, with 1 shifted 11 times. Now, because I'm sort of paranoid, I go ahead and put parentheses around like this. I think order of precedence would let that work without those inner parentheses, but it's just smart and it makes it more readable. And also you should put in spaces. And now you can stand back and I can go, oh, okay, you're clearing bit 23, 17, and 11 and outputting zeros. I can see that right off the bat without a lot of confusion. Whereas if I gave a hex word, so first off, for a 32-bit register, or for a 32-bit port, how many hex digits do I need to describe that 32-bit port? Okay. I need 8 hex digits. That's a lot of hex digits. And I have a lot of trouble in my head knowing what hex digits it would be for bit 23, 17, and 11. I mean, you can do it, but it takes a lot of screwing around, right? So you don't want to do that. Plus, nobody can look at your code and make heads or tails out of what you just did without you specifically telling them. So if you don't comment it real nicely, it's hopeless. Whereas this is very clearly commented. And if you make a mistake, you'll find it here a lot faster than you will looking at 8 hex digits and figuring out which one's wrong, right? So you need to adopt this method. And the nice thing in this chip, if say we were doing this on not using the pin clear output register, but we just wanted to use the port register, and I think it's called port. I think it says port B, port register or something. I don't know. It does exist. You can use it. But if you wanted to clear them, then you'd have to do ampersand, and you'd have to tilde this. But you could do that. That would be fine. And then you'd have zeros at position 23, 17, and 11, and ones everywhere else, and you would only clear those locations and leave everything else alone. But that's a little more screwing around. It's nice to have the pin set, pin clear, and then pin top. And you just OR equals every one of those. Okay? Alrighty. So I will see you on Thursday. And then hopefully on Thursday, I'll make sure I've got all the info on the full LED display, and I'll probably demo that in class as well.
Just look at the yeah, I do. You might be able to.